All right, welcome back. So now we're going to look at some common three-dimensional shapes and their derivatives and second derivatives, okay? Okay, let's start with a plane. Okay, so a plane, we're going to write a plane. There's lots of different ways, and we're going to really, in the next section, we're going to get into equations of lines. Oh no, we've already done that, but we're going to get a little bit more. But one way to write a plane we already know is um, ax plus by plus cz equals d. We're going to take our plane to be, we're going to take and assume that we've done all this, and we're going to write z equals sum ax plus by, okay? Plus, let's say, plus d. Let's write it instead. Z equals negative a over c x minus b over c y plus d over c. Okay, we'll just go straight through like we did. Okay, so what is the first derivative? So this is like saying we've got f of xy equals z. Okay, so f sub x, the partial of f with respect to x is negative a over c. Just right there. Partial of f with respect to y is negative b over c. All the second derivatives are 0. Okay, all the second derivatives are 0. Okay, so that's a plane. Let's look at another one. Let's look at a sphere, which is a little bit different. Let's say we have x squared plus y squared plus z squared equals r squared. Now, what we're going to do when we think about this as sort of, is we're going to do what you may remember as implicit differentiation. Okay, so when we do implicit differentiation, we assume a dependence. So we assume that z equals a function of x and y. Okay, and then we're going to take the derivative of both sides with respect to, let's take the derivative of both sides with respect to x. Okay, so we're going to get 2x. Now, y is an independent variable, so we don't, the derivative of y with respect to x is 0. But z, we've assumed, is dependent on x and y. So 2z partial of z with respect to x equals 0. Partial of z with respect to x is negative 2x over 2z, negative x over z. Okay, let's take a look at what that means. You know, I could have done also for the plane, but that one was a little bit easy, but let's do it. So for the plane, let's look at both these pictures. For the plane, when you have a plane like this, basically you're saying you could write a plane. We've drawn it before. We should have by now. Okay, we've drawn it before. And you know that it looks, you could draw it like this, right? Okay, so at a certain point, no matter where you are, if you go up in x, let's say, you're going to have a certain rise in z. Same thing, if you go up in y, if you go along this direction, you're going to have a certain change in the z direction. Okay? And it's constant. That's what these are saying. For the sphere, it's a little bit different. Let's try that. I'm very bad at drawing spheres, as you know. Let's try it. There we go. Yeah, that's terrible, but whatever. It'll work. Okay, so let's say that you're at a point on the sphere. Let's say that you're at a point, let's say here on the sphere. Okay. Okay, if you move in the x direction, okay, if you move in the x direction, then what's going to happen to the z direction? Well, if you move in the x direction and you're going on the sphere, what they're saying is that your z direction is going to move this way in terms of negative x over z. Okay, let's see if I can do that a little bit better. Let's do instead partial of, with respect to y of this. Doesn't take much, doesn't take a genius to see that partial z with respect to y is just going to be the same thing as what I did there, y, negative y over z. I think it might be a little bit better. Okay, so if I go out here and I move in this direction, let's do it in red. If I move in this direction, right, I'm here, I move in this direction, what's going to happen? It's going to go down like this. If I'm out here and I move, it's going to go down even more. Okay? As your y gets bigger, it's going to move more, and the z is actually getting smaller too. So it's not just linear. Okay, so the change is more as you get farther out along the center. And then as you come here, it's going to go back again. Okay? All right. Let's do a couple more. This one's actually, these next two are my favorite. We're away from implicit. Let's talk about paraboloids. So let's say we have z equals, and let's do this, ax squared plus by squared plus cxy. Okay, so that's a paraboloid. Okay, so now, partial of z with respect to x is going to be 2ax plus cy. Partial z with respect to y is going to be 2by plus cx. Okay, now let's do the second derivatives. Okay, partial squared with respect to x is going to be 2a. Similarly there. Partial squared of z with respect to x, I should do the other way around. This is taking the derivative first with respect to x, then with respect to y. Equals, so that's the derivative of this with respect to y. I'm sorry, this with respect to y is going to be c. That's also c. Okay, so we represent this with a matrix 2a, c, c, 2b. Okay, this is sort of the representation of the second derivative. Our sort of basic examples, there's actually two of them that we're going to talk about. Z equals x squared plus y squared. Okay, in which case, the second derivative is this matrix 2, 0, 0, 2. Okay, and this thing looks like okay, this thing looks like so. I lied, I said 2. There's 3 of them that we're going to look at. There is z equals x squared minus y squared. Equivalently y squared minus x squared, but we'll just stick with one of them. Okay, that one looks like so. Okay, and our second derivative there I say second derivative, I should say second derivative matrix is -2, 0, 0, -2. And finally, we have z equals x squared minus, sorry, that should have been negative x squared minus y squared. Now I'm going to do x squared minus y squared, sorry. Now I'm going to do x squared minus y squared. That one is the hardest one to draw, actually. Okay, so that one's going to be positive in x, but negative in y. So what I like to think of it is it's like you have something going like so. Okay, and this shape is what we call a saddle. Because it looks like a saddle, right? And our second derivative matrix here let me actually move this over. Let me make some of this a little smaller. There we go. And the second derivative matrix here is going to have a positive here. There, okay? So these are sort of 3 main shapes we're going to think about going forward. All right? All right, that's it for this set of videos. I'll see you in the next set.